All right, so for our next example, we see that we have another definite integral, but this time we have some trig functions in the mix here. So we're going to see how we deal with this. Again, the very first thing that we want to do is make a selection of what is going to be our u and what's going to be our dv. Okay. So if we take a close look here, of course, x is going to be real easy for us to take the derivative of. Okay. Also, we know that if I keep on taking successive derivatives of this, I know that I'm going to be able to, terminate this particular derivative whenever I do successions of it. Okay. I'm going to do the traditional way of integration by parts this time, just because here the only time it's really worth it to do the tabular integration is whenever you have the circular integrals, or when you have something like x raised to a power or something that is 2 or higher. Okay. So here I'm just going to let x be u, and we're going to let cosecant squared x dx, let that be our dv. Now, at first glance, we're like, don't know about that, because I really don't want to take the antiderivative of cosecant squared. But when you really think about it, knowing what the antiderivative of cosecant squared is actually easy, because we know that the derivative of cotangent is negative cosecant squared. So that means that the antiderivative of a positive cosecant squared is going to be negative cotangent. Okay. And just in case you forgot that, we can look at this as saying cotangent is cosine divided by sine. And if we take the derivative of that, using the quotient rule says low function times derivative of high. So low function times derivative of high, so that would be minus sine, minus high function times derivative of low, and so derivative of sine is cosine, all that divided by the low function squared. And of course here, this SS means sine times sine, so that'll be sine squared, and of course c times c is cosine squared. So this is like 1 sine squared plus cosine squared. And we all know that sine squared plus cosine squared is 1. And thus 1 divided by sine squared is going to be cosecant squared. And of course I've been carrying those negatives there. So we know that it's relatively easy for us to take the antiderivative of cosecant squared. Okay. So now that we know that, we can go ahead and use our integration by parts formula after we find out what our du and our v is going to be, and just move forward and evaluate the definite integral at that point. All right, so we know that if u is equal to x, then it means that du here is going to be equal to 1 times dx, or just dx. We also know that if dv is going to be secant squared x dx, then that means that v is going to be minus cotangent of x. And so with this being our u and all this being our dv, then that means the integral of u dv. Let's try to make that look a little better. Pen is having a mind of its own today. All right, so the integral of u dv ends up being uv minus integral of v du. Okay. Now, notice that we have definite integrals here, so we're actually going to have to include the fact that this u times v needs to be evaluated from pi over 4 to pi over 2, and same deal here. Okay. So we're going to erase this and make sure that we include the fact that we're actually evaluating a definite integral here. So I'm going to do uv and evaluate that from pi over 2 to pi over 4 minus integral pi over 2, pi over 4 to pi over 2. Got that backwards. Let's try that again. Okay, pi over 4 to pi over 2. This is pi over 2 here. And this is pi over 4. Okay. And this is going to be v du. And of course, u is x. V is minus cotangent x. And we evaluate that from pi over 2. From pi over 4 to pi over 2. I don't know why I want to write pi over 2 first. All right, so pi over 4 to pi over 2. And then minus integral of pi over 4. I did it this time. Pi over 2. And then v is going to be a minus cotangent x. And then du is just going to be dx. Okay. So now that we have that, let's go and work a little more on this now. So here I'm going to go ahead and evaluate what this is going to be. So we'll say minus pi over 2 cotangent of pi over 2 minus pi over 4 cotangent of pi over 4. And then from there, we'll have this minus and minus will give us a plus. And so here we need to be able to evaluate the antiderivative of cotangent. And if I remember correctly, that's going to be natural log absolute value of sine, maybe minus, but I'm going to do it via substitution rule just to double check myself there. So here, what I'm going to do is, let's do this pi over 4, pi over 2, and I'm going to write this as cosine of x over sine of x dx. And so at this point, I'm going to change colors here. Let's use this. We're going to let u equal sine of x. So I'm using substitution rule here. Then, let's try this again. Then we know that du is going to be cosine of x dx. Okay. So we know that all of what we have up here is going to be du dx. So all of this is going to be du, sorry. And what this is going to be is just u. And so now what we would need to do, of course, is figure out what u of pi over 4 is, which that's going to be the same as sine of pi over 4, which is going to be 1 over square root of 2. Or some of you may like to rationalize your denominator and write it as root 2 over 2. And u of pi over 2, so sine of pi over 2 and 90 degrees is just 1. And so here, this would just be 1, and this would just be 1 over root 2. Okay. So now that we have all of that, let's go ahead and also work on what we have here. So move down some here. So therefore, u dv, and I'm going to do this in a different color too. So we know cotangent of pi over 2 is just cosine of pi over 2 over sine of pi over 2. And here, cosine of pi over 2 is just 0. So it doesn't really matter what this is, but we know sine of pi over 2 is just 1. So all of this just ends up being 0. Okay. If we do the same thing, cotangent of pi over 4, that's going to be 1. And that's because of the fact that cosine of pi over 4 and sine of pi over 4 equal to the same exact thing. Yeah, it's not writing the way I want. So let's try to make it do that. And of course, both of these, 1 divided by root 2, 1 divided by root 2, so you end up getting 1. So what we have here is just 1. So now that we have all that, we can go ahead and finish up working this problem here. So we have a negative pi over 2 times 0, so we can just ignore that term. We have a minus times a minus, which is a plus, 1 times pi over 4, so all this just ends up being pi over 4. And then we have plus. Our new integral now is going to be from 1 divided by root 2 to 1 of du over u. And we're going to make that du look a little better here. Wow. All right, du over u. And so now we know that the antiderivative of 1 over u du is just going to be natural log of absolute value of u. So this is natural log of absolute value of u. And we're going to evaluate that from 1 over root 2 to 1. So we have pi over 4 here plus. When we evaluate it at 1, absolute value, natural log absolute value of 1 minus, and then we'll see natural log of 1 divided by root 2. Okay. And we are almost done here. So we know that natural log of 1 is just 0. So the only thing we have to worry about now is the natural log of 1 divided by root 2. But of course, this can be written as natural log of absolute value of 1 minus natural log of absolute value of root 2. Okay, and that's going to be that with the minus on it if we take care of all of that. And again, natural log of absolute value of 1 is just 0. So all we really have here is natural log of absolute value of square root of 2. So from here, all of that just ends up being pi over 4 plus natural log of square root of 2. And we don't need the absolute value signs because square root of a number that is non-negative will always end up being positive. And so at this point, this is the answer. But if we wanted to get fancy, since square root of 2 is 2 raised to the 1/2, we could also rewrite this answer this way if we like. Okay, so this answer or this answer is acceptable. All right, let's move on to the next example. All right, so for our next example here, we actually see that we have something that's kind of similar to what we've seen before. meaning that we have to take the integral of a natural log function. One thing that we want to note here is that since we have natural log of square root of x, that we could rewrite this integral as, and this is because of the fact that we could rewrite natural log as natural log of square root of x as natural log of x raised to the 1/2. And of course, that could be rewritten this way. We know that this integral could be rewritten as the integral from 1 to 4 of 1/2 times natural log of x dx. And so in knowing that, we could rewrite this integral this way. And if you remember what we did back on a couple of examples ago, I think it was like the second example that we did, we actually found out that the antiderivative of natural log of x is just going to be x times natural log of x minus x. And remember, we found that out by doing integration by parts. And so since we see this, we're not going to recreate the wheel again. We're going to use what it is that we already know. And so we're going to use the net change theorem from Cal A and evaluate the antiderivative of natural log of x, which is just x times natural log of x minus x, from 1 to 4. Okay. And I'll come down here and do that. So we'll have 1/2, and then we'll plug in 4 everywhere where we see x. And then after that, we'll plug in 1 everywhere where we see x. Okay. And of course, we know that natural log of 1 here is going to be 0. Oh, let me not do it in that color. That's a little too bright. Let's do it in red. So we know natural log of 1 is 0. And of course, 0 times 1 is 0. And 0 minus 1 is -1. But we have a negative times a negative here, which is going to end up being a positive. So when we move down, write this again, we know this is going to be a +1 here. Now over here, we could choose to leave this as natural log of 4 times 4 minus 4, or we can go ahead and multiply that 1/2 through. What I'm going to do here is just write this down as is for this step. And then from here, we will go ahead and just multiply the 1/2 through to all those terms. So before I do that though, I'm going to go ahead and simplify this to -3 and then multiply on through. So this will be 2 times natural log of 4 minus 3 over 2. And of course, this is 2 times natural log of 4. We can put the 2 up in the exponent here. That'll be natural log of 4 squared, or natural log of 16 minus 3 over 2. So this will be a simplified version of our final answer. Of course, 2 times natural log of 4 minus 3/2 is acceptable too. I personally just like to condense down the logarithms as much as I can, just because of the fact that if you're actually going to use that expression in the calculator to figure out what the actual number is, natural log of 16 is a little easier to type than 2 times natural log of 4. All right, let's move on to the next example. All right, so for our next example here, we have another definite integral, but this time we're asked to find out what the integral is going to be, where the integrand is a product of two functions that end up having those circular integrals like what I was talking about before. Okay. Now we see here that s is the variable and t is a constant, so we have to make sure we remember that when we do our integration or take derivatives or whatnot. But in this case, we're going to use tabular integration to do this because of the fact that we do have this circular type integration going on here. So what we're going to do is make our columns for u and dv. I'm going to say let e raised to the s be u, and sine of constant value t minus s ds, let that be our dv. Okay. And so what we're going to do again is take successive derivatives of column u and successive antiderivatives of column dv until we see something diagonally across that says e raised to the s times sine of t minus s again. Okay. So we know that the derivative of e to the s with respect to s is just going to be itself. So that's easy. If we take the derivative, the antiderivative of sine, that's going to be a minus cosine. And then, of course, from here, we need to take whatever the derivative of t minus s is going to be. And remember, and this is because of the substitution rule, t is a constant, so the derivative of t is 0. And, of course, the derivative of minus s is just going to be a minus 1. So if I took minus 1 and divided it by this, a minus divided by a minus is going to give me a plus. And since we're going to do this again, we're going to put another ds here since we're going to take the antiderivative again. All right, so next row, the derivative of e to the s is e to the s. And here again, if we take the antiderivative of cosine, that is going to be sine. And again, the derivative of t minus s is going to be just a minus 1. So we're going to put a minus here and then put the ds again. All right, so notice here that I'm only putting the ds's here for formality because we're doing tabular integration and this is going to end up being successive. The only ds that I'm actually going to really need is this last one here. So I'm just going to erase these other two because I don't want to complicate things. So we're going to go ahead and do our diagonals here. And we know at this point, since we see e raised to the s, sine of t minus s in here, we know that we'll stop. And so we'll use this particular term to integrate and stop. In other words, this last term here will actually have an integral sign in it. And of course, since it's a definite integral, it'll end up being integral from 0 to t. So looking at this, we know now that integral of 0 to t of e to the s times sine of t minus s ds, all of this is just going to equal. And I'm going to hold off a minute on how I actually write this as far as the definite integral part of it. I'll wait to the very end to kind of put all that together. So here I'm just going to say e to the s times cosine of t minus s. It's going to be e to the s times cosine of t minus s, like this. And then minus. So we have minus a minus, which is going to be plus e raised to the s sine of t minus s. Yeah, pen is starting to drag again. And so for these first two terms here, since we're not going to have an integration sign on it, what we want to do is write it like this, meaning that we've already gotten what the antiderivative of those terms are. well, these terms are antiderivatives, and so we just need to evaluate them from 0 to t. Now, for this last term, since we're going to terminate the amount of terms that we write with this last one here, of course, we have plus here, but we got plus a minus. So it's going to be minus here, integral from 0 to t. And it's going to be e raised to the s times sine of t minus s ds. Okay. And so now that we have that, then of course here, what we see is I can take this term and I can add it to both sides. So if I add this to both sides, I'm going to have a positive one of these plus another positive one of these, which is just going to be 2 of these. Okay. And so, of course, from here, what I have left is I have this antiderivative, but of course I got to evaluate from 0 to t. And so I'm going to go ahead and take care of that now. And I'm going to plug in t everywhere where I see s. So it's going to be e to the t cosine of t minus t plus e raised to the t sine of t minus t. So that'll be the first term. Not first term, but these will be the first terms. And now we'll do the same thing again with 0. So I'll have e raised to the 0 cosine of t minus 0, which is just cosine of t, plus e raised to the 0, and it'll be sine of t minus 0, which is just t. And again, we know that e raised to the 0 here is just 1. And here we know that t minus t is 0, and cosine of 0 is 1. Sine of 0 is 0, which makes all that 0. Okay. And so I'm running out of room here, but what we can see from this is I have an e raised to the t out of all this, and then I have a minus cosine of t minus sine of t here. And so I'm going to actually write this up here now. So here we know that our final answer is just going to be just this integral here, so we'll need to be able to divide by 2. So I'm going to take all of this and divide it by 2 as well. I'm actually going to come up here and write the final answer. And so here, integral from 0 to t of e to the s sine of t minus s ds. Here, that is just going to equal here, and this will be 1/2, and then in this first term here, e raised to the t, and then we have a minus cosine of t, and if we distribute that minus to the second term, it'll be a minus sine of t as well. And that would be our final answer. Of course, if you want, you could factor out the a -1 out of each term. Not necessary that you do this, but just depending upon if you want the answer to look a different way here. If you factor out the negative, then it will look like that. Either way, answer is fine. All right, so let's move on to our next example here. And so we see that for this example, we're kind of being asked to use the substitution rule first before we actually apply integration by parts, because it may make life a little easier for us. So we will go ahead and do that. So if we're going to do that, then let's let u equal x cubed, because that's the innermost function here. So we let u equal x cubed, then that means du is going to be 3x squared dx. And matter of fact, let's not make this u, let's make this w. Just because whenever we do integration by parts, we'll be using u for that. And here, this means that dw over x squared is actually going to be equal to dx here, okay? So if we go and substitute what we need to here, we'll have x raised to the 5 times cosine of w, and in place of dx, we're going to have dw. Let me draw that again here. So I'm going to have dw over 3x squared. Okay. And notice here that the x to the 5th over 1 here, and the x squared down here gives us a net x cubed in the numerator times cosine of w dw. And of course we have an extra 1/3 because 3 is in the denominator here. I'll just write it like that for now. And here we'll go ahead and factor out the 1/3. And remember here that x cubed, we don't want this here, but remember that x cubed is indeed w. So we could replace that with w times cosine of w dw. And so we see by using the substitution rule, we still have to do integration by parts, but we're only going to have to do it once because we have it in this form. And because of that, now we can go ahead and apply integration by parts. And let's switch colors here. And we're going to let w be u here. And we're going to let cosine of w dw, let that be dv. Okay. And because of that, then that means that du is going to be dw, because derivative of w with respect to w is just 1, so there's 1 dw. And v here, we know that the antiderivative of cosine of w is going to be sine of w. Okay. So now that we have all of that, then we know that this is just going to be 1/3 integral, well, sorry, let me back up here. 1/3, and of course I'm going to write the formula in here, uv minus integral of v du, and our u is w, our v is sine of w, minus integral, our v again is sine of w, and our du is going to be dw. Let's try to make that look a little better. Okay, and of course, since we're doing an indefinite integral here, all of this is going to be with a plus c at the end. Okay. All right, so therefore, x to the 5th cosine of x cubed dx, because that's what it is that we're trying to solve here. It's just going to be 1/3 times. I'll leave everything in W until we're actually done doing our integration here. So we see here that the antiderivative of sine is going to be a minus cosine, but a minus cosine times -1 gives us a positive cosine, W, and all that plus C. And so from there, we'll now go and substitute back x cubed where we see W. So that'll be x cubed sine of x cubed plus cosine of x cubed, all that plus C. And let's make that x look a little better. And we see that that ends up being the answer that we need to get. And so because we use the substitution rule first, that actually made using integration by parts relatively simple here to use and employ so that we can get our final answer. And so this is an example of how we can actually use the substitution rule. We've been using it a lot actually, but in a more traditional sense, using the substitution rule first and then using that to be able to perform integration by parts on the integral of some function. Okay, so for our last example, we're going to do